Thanks for watching my video today. We are going to discuss three identities from binomial theorem. Okay, so the identity 1 will be the sum from k equal to 0 to n, and combination of k equal to 2 to the power of n. Okay, so this is the first identity we are going to prove here. So let us prove. So we know that here we are going to use binomial theorem. Okay, so we know that 1 plus x to the power of n equal to, I'm going to write it in summation form. Okay, so this will be the sum of k equal to 0 to n of n combination of k x to the k. Okay, so I'm going to keep the link of how we prove this one. Okay, so check out in my description box. So putting x equal to 1, we get here in that binomial theorem. So if you put x equal to 1, what do we get? 1 plus 1 to the power of n equal to the sum from k equal to 0 to n of n combination k of into 1 to the power of k. So we know that 1 to the any number, any power to the power of 1 will be always 1, right? 1 to the any power will be just 1. So k, the sum from k equal to, let us interchange that, k equal to 0 to n of n combination k, and 1 to the k is just 1. Okay, so into 1 plus 1 means 2 to the n. So this is the first identity. Okay, now let us expand the sum. Okay, let us expand this sum, and let's see what is going there. So if I expand that n combination of 0 plus n combination of 1 plus n combination of k, n combination of 2 plus, and so on up to n times, right? So up to plus n combination of n equal to 2 to the power of, and here this sum depend on n, right? If you put the value of n, any value, then you'll get, okay, the sum of that will be, you'll get 2 to the n, okay. So this is the first identity we are to prove, okay. So okay, so now the next one will be our second identity, okay. So number 2, the sum of the number 2 will be sum from k equal to 0 to n of k into n combination of k, okay, equal to n into 2 to the power of n minus 1, right? So this is the second identity we have to prove, okay. Here in that combination k is there, right? So now let us prove. So here we are going to use the same logic, okay, with 1. So we are going to use that binomial theorem, okay. 1 plus x to the power of n equal to the sum from k equal to 0 to n of n combination k into x to the k. So the first identity is putting x equal to 1, right? But for the second identity, since k is there, so we are going to take the derivative, right? So differentiating with respect to with respect to x on both sides, okay. So we get differentiating only one time, okay. So we know that differentiation of x to the k is k into x to the k minus 1, right? So differentiation of 1 plus x to the n is n 1 plus x to the power of n minus 1 using chain rule. So so since we differentiate already n times 1 plus x to the power of n minus 1, and differentiating 1 plus x, we get just 1, right? So in is that 1 n times 1 plus x to the n minus 1, and since differentiation is done with respect to x, so the summation and that combination will be constant, right? So that means it will come out n combination k, and we know that differentiation of x to the k is k times x to the k minus 1, because differentiation is done with respect to x, so meaning k will be constant, right? So here we get what we are to prove, okay. We get already here. Now putting x equal to 1, we get, what do we get if we put x equal to 1? So n times of 1 plus 1 to the power n minus 1 equal to the sum from k equal to 0 to n of combination n k, or n combination k into k into 1 to the power k minus 1. We know that any 1 to the any power, if 1 to any power will be just 1, right? So I'm going to interchange the sum again. So there will be, so the sum from k equal to 0 to n into k times k into combination of n k, right? Or n combination k, okay, which is equal to n times 1 plus 1 means 2 to the power of n minus 1. So this is the proof, okay? So this is our right answer, okay? So this is the proof. Now let us try to expand that sum, okay, and see what is going on there, okay? So let's expand let's expand the sum, okay? So summation means nothing but plus, right? Positive. So since the sum is starting from k equal to 0, right? 0 into n combination of 0 plus 1 into n combination 1 plus 2 into n combination of 2, right? Plus, and so on. Here that 0 will get cancelled out, right? So that means our sum will start from 1, right? So and plus n into, since our sum is from, our sum goes to n time, okay? N times or n time. So n into n combination of n equal to, so that sum will be, or answer will be n times 2 to the power of n minus 1. So if you put the value of n, any number, right? So you'll get that the answer will be that n times 2 to the power of n minus 1. So hence proof. So this is our second identity proof, okay? Okay, now let's start our identity 3, okay? The proof of our identity 3. So 3 will be a little slightly different only, okay? 1, 2, 3, they are only slightly different. So our identity 3 will be the sum from k equal to 0 to n into times k square into combination of n k, okay, or n combination of k. Here the first identity is without k, the second will be k, and third will be k square, right? Which or sum this will be nothing but n into n plus 1 into 2 to the power of n minus 2, right? So the same logic will be applied here, okay? 1, 2, 3 logic, okay? The identity 1 and 2, the same will be using here, okay? So we know that from binomial theorem, so 1 plus x to the power of n equal to the sum from k equal to 0 to n of combination of n k, okay, or n combination k x to the k. Here we are going to apply the operator here. Operator means just nothing, okay. We are going to apply on both sides this one, okay. X times d by dx, okay. X into differentiation of d by dx we are going to apply here on both sides, right? So apply the operator x d by dx both sides. So we get, what do we get? X, and what do we get will be x into d by dx 1 plus x to the power n equal to x d by dx of the sum from k equal to 0 to n of combination of n k or n combination k into x to the k, okay. Now we are since here we apply that operator, okay, x d by dx. Now the step will be different. We are going to differentiate now, right? X into differentiation of 1 plus x to the n is n into 1 plus x to the power of n minus 1, right? And differentiation of 1 plus x will be 1 is 0 and x is 1, right? Using chain rule, okay. And since the sum and that combination is constant with respect to x, right? So they will be coming out. So the sum from k equal to 0 to n of n combination k into k into x to the k. Here I'm just shortening it, okay. Here the x to the k minus 1 will be, right, it will be x to the k minus 1, but here we have here x again, so that x and negative 1 x 1 by x will cancel out, so we get x to the k, okay. Now differentiating or differentiate with respect to x, we get, now we are going to differentiate again. Here we are going to use product rule, right? Product rule. Since n is constant, okay, now we differentiate x only, okay. 1 plus x to the power of n minus 1 plus differentiation of first function into second function will be first function differentiation of first function times second function to differentiation of first function plus first function to differentiation of second function, okay. That product rule we apply here, plus n minus 1 into x into 1 plus x to the n minus 2, right, which is equal to, here if you differentiate that sum part, okay, so the sum from k equal to 0 to and since differentiation is done with respect to x, so the sum and that combination will be constant, right, up to n. The sum from k equal to 0 to n times of combination of n k into k square into x to the k minus 1, right? So if you differentiate x to the k and k will be k square, right? Now putting here, since we are putting x equal to 1, we will get our required answer, right? So putting x equal to 1, we have n into 1 plus x will be 1 plus 1, which is 2 to the power of n minus 1 plus n minus 1 and minus 1 into x is 1, here 1, just 1, right? 1 plus 1, 2 to the power of n minus 2, which is equal to the sum from k equal to 0 to n times k square into combination of n k, and 1 to the k is just 1, right? Now let us interchange that sum and the left hand side and right hand side only. So the sum from k equal to 0 to n k square times combination of n k, okay, which is equal to, now here we are going to simplify only a little bit, okay, n into, or n times, okay, 2 to the power of 2 into 2 to the power of n minus 2. In order to get n minus 2, okay, so I'm going to just multiply by 2 only, right? Here n minus 1, so to get n minus 2, we just multiply it by 2, so 2 into 2 times 2 to the power of n minus 2 plus n into that opening that first bracket, so n into 2 to the power of n minus 2 minus 2 to the power of n minus 2, right? Now what do we get? N times that 2 to the power of n minus 2 and 2 to the power of n minus 2, the coefficient is 1 is that one will be 2 and the other one is 1, right? So 2 minus 1 is just 1, so it will be 2 to the power of n minus 2 plus n into 2 to the power of n minus 2, right? So here we have 2 to the power of n minus 2 common on both, common on that 2 term, okay, 2 terms, so we are going to just take it out as common, okay, and so n times n plus 1 to the power of n minus 2, okay. So this is our proof, okay. So let's write it down. The sum from k equal to 0 to n k square combination of n k which is equal to n into n plus 1 into 2 to the power of n minus 2. So we're here, if you see the both three of the identities, right? Three identities. So we can generalize it, right? So the generalized will be coming soon. Okay, I will do the other video for generalized one. Okay. That the generalized one will be here. For the first identity is just without k, okay. The second is one is k and the second is k square. So that's it. Thanks for watching my video. Please subscribe, like and share.